Welcome. In this video, we're going to be looking at 11.1, which is all about lines that are intersect circles. And we are going to be looking at some different types of lines, segments, and how they relate to circles. So to start off, let's just define a few of these different ones. So our first is a chord. So chord is any segment that has endpoints on the circle. So AB, segment AB, here would be an example of a chord in the circle. A secant is a line, so notice that difference here, that intersects a circle twice. So this line L is a secant. Okay, line AB would also be a secant if we continued on in both directions through A and B. So this is line L notation. I would just have the letter. A tangent is a line, or it could be other objects. We're mostly going to focus on lines that intersects the circle exactly once. So think about if you have your circle and you're bringing a line right up to the edge of your circle, so it just touches the outside of your circle, that is a tangent line. Okay, the point where the line touches your circle is called the point of tangency. So this line M here is a tangent line, and the point of tangency is that point C. Okay. With these types of lines and segments, we have some different relationships within the circle itself. So we're going to look at three different theorems today. The first one is about a tangent line. So if we have a line and we know it's tangent to a circle, then we can conclude that it is perpendicular to the radius at the point of tangency. So if you know you have a tangent line and you know your point of tangency, if you draw in your radius there, that radius is perpendicular to the tangent line. Okay, the converse of this also works. If we know that we have a line that's perpendicular to a radius at a point on the circle, then it is tangent to the circle, right? I could draw lots of lines that are perpendicular to this radius, but it has to be at that point on the circle. Okay, and finally, we have some segments. If we have these segments set up like this, where we have two segments that are coming from some common endpoint, tangent to a circle at their other endpoints, these two segments are congruent. So anytime you have two segments coming from a common endpoint that just touch the circle at their other endpoints, so if you continued on this line AC or this line AB, it would not cross your circle again. Okay, so we have those relationships. Let's look at some examples with those relationships. So first here we have just a circle with all of these different things. So let's first identify just some different things. So we might not get all of them, but we'll at least get some. So if we're going to look at a chord, an example of a chord here would be QR. And remember, chords are segments, so we're going to label it as such. We could also call ST a chord, as long as we're talking about the segment ST. It's a particular chord, it's a diameter, but it is also a chord. So we could also say that this is also a diameter. We have a secant. Really only one option here that's drawn as a line, and that would be ST. It's a line. You could also call that line SP or line PT, line TS, right? All of those are the same line. Tangent line here. We have UV, and the point of tangency is the point U. I think the only other thing here we have interesting to talk about would be PQ. PQ is a radius. Okay, so all of those different things we should be able to talk about, identify within our circles. Okay, number two, we're looking at identifying the point of tangency and writing an equation for a tangent line at this point. So we have these two circles, circle D and circle C, and then we have this line here that just touches both circles there. So that point of tangency is at the point 2, -1, and it's this nice horizontal line. So if you forget horizontal lines, think about some points here. We already said it goes through 2, -1, but it also goes through 0, -1, and -1, -1, and -3, -1, and 4, -1. What do all of those points have in common? They all have a y value of -1. The line is just y equals -1. Okay, two more examples. Next one, we have this ice cream cone looking thing. So we have two segments that are tangent to our circle at points E and F from a common point D. So we learned earlier that means that these things are congruent, which means their lengths are equal. So if we know DE is 2y squared minus 4y and DF is y squared minus 3, those segments are congruent. So we can set those equal to each other. Right, and then we think, we have a quadratic, so we should probably just get everything on one side. So we get y squared minus 4y plus 3 equals 0. So we have some options here. We could use the quadratic formula if you wanted to. We could see if we could factor if we wanted to. We could guess and check. It might be a little tedious. So let's see if we can factor this because we have an a value of 1. That's usually a good choice there. Multiplies to be 3 and adds to be -4. Oh, that does factor. We get y minus 3 and y minus 1. Right? -3 times -1 is 3. -3 plus -1 is -4. If you multiply this back out, you get back there. We're going to use our zero product property. If these two things multiply to be 0, that means y minus 3 has to equal 0, or y minus 1 has to equal 0. So we get y equals 3 or y equals 1. So let's check these and see if they work, right? These are segments. So if we were just doing an algebra problem, we would be done. Those would be both of our answers. But since this is a geometry problem, we have to check and see if these work. So if I take these and plug them back in, let's try it here. 3 squared minus 3. We get 9 minus 3, which is 6. Hopefully we get the same thing here. I'm going to use my calculator because why not? If I do 2 times 3 squared minus 4 times 3, I'm really hoping that I get 6 as well, which I do, which is awesome. Okay, so that guy works. Let's see if 1 works. 1 squared minus 3, I get -2. Can the length of a segment be -2? No. So y is 3. So we can use our algebra skills within our geometry as well there. Very last one we're going to look at here. Early in flight, the Apollo 11 orbited the Earth at an altitude of 120 miles. What was the distance from the spacecraft to the Earth's horizon to the nearest mile? The radius of the Earth is approximately 4,000 miles. Okay, so I'm going to try and draw a decent picture here. So we have the Earth, which we are going to approximate as a circle. And I know it's not exactly, but that's okay. So if we look at the Earth here, they tell us that the Earth's radius is approximately 4,000 miles. So that's going to be important. And it says early in its flight, the Apollo 11 orbited the Earth at an altitude of 120 miles. So we're not far off in comparison here. We're like up here just ever so slightly. Okay, and that ever so slightly there is the 120 miles, and that's probably even an overestimate there as well, but that's okay. And we want to know the distance from the spacecraft to the horizon. So the horizon is where you lose sight of the Earth, so that's where you're actually reaching a point of tangency, which is a cool application of our point of tangency. So I'm going to try and make this look as decent as possible. So we'll say our point of tangency is right there, which is not going to look, oh, it's actually not too bad. So if I put in another radius, that point of tangency, we learned this in this lesson, is perpendicular to your radius at that point. It's a circle, so our radius is constant. So that's also 4,000 miles. So what we're trying to find here is the distance from the Apollo 11 to the horizon there, so that distance there. So now we have a nice little right triangle. We can just use our Pythagorean theorem. So our hypotenuse is the 4,000 plus 120. So that's my c squared equals a squared, which is one of my sides. We'll do 4,000 plus x squared, which is the other leg of my nice little triangle there. So 4,120 squared gives us that big number. We're going to subtract 4,000 squared. And we get that x squared is 974,400. So to get x by itself, we're just going to take the square root of that, which is 987, and ask us to the nearest mile. So we'll say 987 miles. Okay, which again, my picture's not perfect there by any means, but hopefully that in comparison to your 120 could seem reasonable for where your distance is. So that is all for this video. Thank you so much for watching.